is we have flag complexes of a graph. So the flag or clique complex of a graph has the vertices of the graph as the vertex set, and any subset of the vertices that induces a complete graph is a simplex in the flag complex. So if then there is an independence complex of a graph.
Maybe you want to say what G bracket S is.
Oh, it is the graph induced by by the subset of vertices.
Everybody understands what a induced subgraph means?
I am.
Yes, ma'am. Yes, ma'am.
Okay.
Yeah.
Anybody who doesn't know the meaning, please stop in between and ask. Huh?
Yeah, sure.
Okay, go ahead.
Yeah, so it's induced subgraph. If the induced subgraph is complete, then that set of vertices is a simplex in the flag complex. And you have an independence complex where the subset of the vertex set is an independent set. So an independent set of vertices is a set of vertices that don't share an edge between them. So there is no edge in those in that set of vertices. So obviously, if you have a graph G and you have some subset of vertices, if those vertices induce a complete graph in G, then in G complement, it will be an independent set of vertices. So it's clear how the clique complex or flag complex of G is isomorphic to the independent graph of the complement of G. One second. Okay. Oh, never mind. Yeah. So flag complexes are very common. Most of the other descriptions in this chapter are also some kind of flag complex. So
just to make sure, G bar means the complement of G, right? Where edges goes to non-edges.
Yeah, the complement.
Okay, fine.
Yeah. So you just include every edge that is not in the graph and you remove all of the edges. The complement of the edge set.
Also, everyone knows what an independent set is?
Complex. I described it. So it's a set of vertices where there are no edges between those vertices in that graph.
Okay.
Right. So if that subset induces a complete graph in G, then in G complement, that is an independent set. Okay. So this is an ordered complex. So the ordered complex of a partially ordered set P is the abstract simplicial complex with vertex set P, and finite chains of P are the simplices of the ordered complex.
Sorry to interrupt, Mrinal, again. I think you're on a different slide right now. We are still seeing the simplicial flag complexes slide.
Oh, okay. That's... No, as far as I know, you are seeing the ordered complexes. That's what I can see that I'm sharing. Is there lag? I'm not sure what's happening. You can see ordered complexes now, right?
Now we can, but when you were discussing about the order complexes, simplicial, is it happening just with me or others are also seeing it? Probably there is some problem with my network connection today.
No, ma'am. So before this, even I could see the simplicial flag, the first slide. Not
this one was not coming. Yeah, I think so. Okay. Mrinal, possibly what is happening, you have to switch once in between when you change the slide, and then only it is updating the slide.
Yeah, I'll make sure that I go to the Zoom page and I make sure that it's changing the slide from next time.
Yeah.
Right now you can see ordered complexes, right?
Correct. Yeah.
So for a partially ordered set P, the ordered complex of P is the abstract simplicial complex with vertex set P, and finite chains of P are as simplices, including the empty chain. So again, any partially ordered set you can show as a graph. So this is also a special case of a flag complex. And So if the set is a totally ordered set of n elements, then every subset of A is a simplex. So it's just the simplicial complex delta A. So yeah, there are a few examples of where this is used, of where ordered complexes are seen. So yeah, can you see examples of ordered complexes? Do you see the partition lattice? Ma'am, can you please tell me if the slide is clear?
Yeah.
Yeah? Okay. So a partition lattice is an example of an ordered complex. So the elements of the partially ordered set are partitions of the set n, and the partial order is refinement. So this, in this diagram, you have the partition lattice with n is 4. So the minimal element is the singleton partition, and the maximal element is n, is the set n over here. So okay, yeah. So subspace arrangements are another example of ordered complexes. So a subspace arrangement is a collection of subsets of RD or C. So this is real or complex, which I kind of messed up in the slide. So it is a collection of subsets of RD or CD, finitely many linear subspaces of RD or CD, such that no subspace belongs to another subspace in the collection. And the intersection lattice of a subspace arrangement is the poset whose elements are intersections of subsets of the collection, and the order is given by reversing inclusion. So the minimal element is KD, so either, whether, depending on whether it's a real or complex subspace arrangement, it is either RD or the complex number. And the maximal element is the intersection of AI in A. So there is, in the book, actually, there is some more given on subspace arrangements, but I didn't really understand parts of that. So maybe if you could help me with that later. But most of it is just the definitions. Anyway, yeah. So another example is for a group G and prime P. There are two partially ordered sets that can be defined to make ordered complexes. So one is the poset of all non-trivial P subgroups of G, and the other is a poset of all non-trivial elementary abelian P subgroups of G. So naturally, if G is a subset of SP of G. So a P subgroup of G is a subgroup of ordered P to the power n, of some ordered P to the power n. And the order is naturally whether inclusion. So if, well, not just inclusion, it has to be a subgroup of the other. Yeah, I think that makes sense. So there have been attempts to try to understand the connections between the group theoretic properties of families of subgroups and the topological properties of the order complexes of these posets. The order complex of AP of G and the order complex of SP of G are homotopy equivalent. I'm not sure how this is true. It's just stated, but I don't actually have the proof of this. So yeah, wow, this is a lot slower. So this is another prominent combinatorial procedure used to describe abstract simplicial complexes. So you have some collection of combinatorial objects omega, and there is some equivalence relation. So there is some isomorphism defined on omega, and there is a map F from omega to subsets of some universe set V. So for example, if our omega is a set of directed graphs, directed graphs, and on n vertices, and the isomorphism is as you usually define the isomorphism on graphs, and the universe set is the set of edges, then obviously there is a map F from a directed graph to the set of edges that represents that graph. And so then you have some collection C of isomorphism classes. In this case, say we have the set of directed forests for some graph G. Then sigma, some subset of, in this case, V is the edge set, so some subset of V is a simplex of delta C if it is a subset of some f of A for some A whose isomorphism class is in C. So in this case, in the case of directed trees that I was describing, if you have a directed graph G, then the simplicial complex of directed trees is has vertex set, edge set as the edge set of G, and subsets of the edge set that when viewed as a graph is a directed forest are simplices in the complex of directed trees. Then similarly, you have the complex of disconnected graphs. Again, you get it in the same way. So omega in this case is the collection of graphs on n vertices, and C is the collection of disconnected graphs. So yeah, this complex of disconnected graphs on n vertices is homotopy equivalent to the partition lattice. That was an example in the order complex. Again, all of these results are just kind of stated in the chapter, and I tried to find some proofs, but I wasn't very successful in that. Oh, 1 second. Please tell me if I forget to change the slide, if you are not seeing the same slide. So the next is neighborhood complex of a graph. So this idea was one of the first that was used to export topological ideas in theory. So the neighborhood complex of a graph G has vertex set as the non-isolated vertices of G, and simplices are subsets of V that have common neighbors. So the maximal simplices are for some vertex, the neighbors of V, those are the maximal simplices of the neighborhood complex. So for some arbitrary subset of vertices A, you have n of A as
Mrinal?
the set of vertices that have, yes?
So I think you were not present
Yes.
in last talks, but neighborhood complexes has been covered. So maybe you can skip this and move forward. If you have any results to show about neighborhood complexes, it is good.
No, there is just one result.
So just come to
which
the
is
result
that
directly. We all know the definition.
the result is just that the boundary of neighborhood complex collapses onto the Lovász complex. But I have the result. I don't have a proof for the result because none of this. I think this is what was covered. Was this covered? That the boundary of the neighborhood complex.
So have you defined Lovász's
onto the
complex?
Yes, that was what I was leading up to. Have you covered Lovász complex?
No.
Because
so directly start defining the
So-
Lovász's complex and then we can try to see this.
yeah,
Okay.
so from the neighborhood complex, you have a map from the phase set of the neighborhood complex to itself, which is an order reversing map. So this map is used to get Lovász's complex, and again, I've tried to find more about Loveage complex, but I didn't really get a lot of information. I know that um, both of these structures are used to find, I think, bound on the chromatic number of a graph, but I'm not sure about how that's actually been done because, like I said before, this chapter is just a list of definitions, at least the first half of the chapter. Okay, so I'll move on to complexes defined from metric spaces.
Sorry
So
to interrupt again.
for yeah.
What is the normal n in the definition of Lavoisier's complex?
Yeah, so that is so the map
Can you go
of
back
the
in the slide?
yeah here. So n, the normal n maps the simplices in the neighborhood complex to simplices in the neighborhood complex. So if A is some subset of vertices, then n of A is the intersection of n of the neighbors of V where V belong to A. So it is the set of vertices that have A as common neighbors. Does that make sense? Is that clear?
Yeah, okay.
Yeah. So it's an order reversing map, which I will try to explain, but I should have something to
So
write.
let's go bit by
So
bit. You
this
started with the graph G. You
yeah,
constructed its neighborhood complex.
yes,
Then you looked at its face poset.
yes,
And then from this poset
yes,
to itself, you're defining a map which you're calling as N.
yes,
And what you do is
yeah.
you
So
send
this
any
map
element in the F.
reverses the order of the poset. Yeah, you send a simplex in the face poset of the neighborhood graph to another simplex in the face poset,
Which
which
another
is
simplex?
so it is the set. So if um I should be able to draw to give an example. So if you have if your face poset is a single vertex, then it would go to the neighbors of that vertex. If it is two vertices, V1 and V2, then it would be the intersection of neighbors of V1 and so common neighbors between V1 and V2. So for some set of vertices A, it is common neighbors of all the elements of A.
Okay.
So neighbors that are shared by every element in that set. So it reverses the order that the poset has, that the face poset has, because
So are you
it
saying that
maps.
this N is actually defined on just the zero cells and then you linearly extend it?
I don't know what that means.
Just read the last line which you have written in your slide.
Yeah, it's N is defined on, so N is defined in the second last line, right? So N of some subset
So see
A
the map
is the
N.
intersection. Yeah, N is from the face poset of neighborhood complex to itself, to the face poset of the neighborhood complex. That is all. See, this is all that was given in the book as well. So I don't have more to go on than
You
what I
didn't
am
find
saying.
anything about neighborhood complexes anywhere on.
I found a lot
Yep.
about neighborhood complexes. I found nothing about Loveage complexes. So I found nothing about this map because this map is only used to get the Loveage complex. I have also been struggling with this chapter because it is just these random examples with almost no context given, and I have not been able to find context otherwise on the internet as well. So
You could
I
have
really
written to
don't know,
me, but it's
especially with
okay.
this. Okay. Yeah.
Ma'am, I think it is the same app CN as I had mentioned in my presentation, right?
Yeah.
The N there. So just mapping subsets of n of g into neighborhood complex into its this thing, a common neighborhood.
Yeah, that's what it is doing.
Okay, fine. So that f here in the last slide, that just means subset of this thing, right? N of g.
You're just converting the
F
simplicial
is
complex
the phase
back to the
poset.
phase poset. Because when you want to work on any ordered sort of a structure, you want a poset, no? And here posets
Okay.
are being
Yeah.
defined in the sense of whenever they have common neighbors. So that sort
Yeah.
of a tree structure you want. I shouldn't say tree, but this is how you want to build the structure for your poset. And that's why she had to transfer her entire data to the phase poset because it
Yeah. So
captures the entire
Yeah, you can't
information.
just use
this f
um,
here,
the complex itself.
this f here means the power set of n of g, right? F.
No, it's the phase
Oh,
poset
okay, fine.
of
Sorry.
N of
Okay,
G.
fine.
Yeah, should I move on from this?
Yeah, sure.
I mean, I understand that it's not really describing much and the structure is not clear, but like I said, I don't have anything else. Yeah, so then you have complex defined for metric spaces. So for a metric space M, the check complex of a set S of given some positive epsilon is so the vertex set is S, and subsets of S where the intersection of epsilon balls around the elements of that subset are non-empty are simplices of X of the check complex. So the Rips complex is similar, but in this case you check for pairwise intersections instead of intersection of all the balls in the subset in the simplex. So Rips complex is also a special case of a flag complex. So frequently it's used to vary the parameter epsilon and study various filtrations of the simplex. So this diagram has, so the one on the right is the Rips complex and the one on the left is the check complex. So yeah, the check complex is definitely contained in the Rips complex, but the Rips complex is easier to find because you only have to do pairwise checks. Anyway, so then you have the Delaunay triangulation, which is for finite set of point P in a metric space M. The simplicial complex, the Delaunay triangulation is a simplicial complex with vertex set P, and the simplices are subsets of P sigma such that there is an empty ball in M so that all of the points in sigma lie on the boundary of the ball, and it is empty in the sense that no other point P is in the interior of the ball. So Delaunay triangulation, Rips complex, and check complex are often too large to handle. Once the dimensions are 3 or more, they get really, it becomes very expensive to calculate. So the witness complex is an attempt to make that easier. So you have two sets of points in M. You have a set of data points A, and you have a set of landmark points B. I have seen some instances where the set of data points is dense in M, but I have seen others where it's not. So I don't know if it's necessary, but in some places I've seen that the set of data points A has to be dense in M. Okay, so usually, but you assume that there are more data points than landmark points in general. So a point W in A is said to witness subset tau of B if tau is closer to W than to any other element of B, not including elements of tau. So the witness complex given by A and B is the set of subsets of B that have a witness in A. So whenever you have a subset of B, so that there is some point W in A, so that every point of that subset is closer to W than to every other point in B, not including the points in the subset itself. So in concrete successful applications of the witness complex, the important thing to consider is how you choose the landmark points. And apparently there are a lot of interesting ways of doing that, but I am not familiar with any of them. So then you have usually simplicial complexes are defined by defining the simplices, but sometimes it's more succinct to describe forbidden patterns. So that's done using minimal non-simplices. It's a dual presentation of a simplicial complex. So if A is not a simplex, then any set B containing A is also not a simplex. So for instance, in the case of flag complexes, the minimal non-simplices are pairs of vertices that are not connected by an edge. In case of directed forests, minimal non-simplices are pairs of edges that have the same end vertex and all directed cycles. In the case of disconnected graphs, the set of spanning trees is the set of minimal non-simplices. So in some cases, it is easier to use the minimal non-simplices representation. One case for metroids, it is both descriptions of the complex are of simplicial complex from metroids are used very frequently. So the simplicial complex description uses independent sets. So for a metroid on a finite ground set V, a metroid on a finite ground set V is a non-empty collection of subsets of V, such that first of all it has inheritance properties. So if sigma belongs to I, then any subset of sigma belongs to I. And the second thing is that if you have two elements sigma and tau of I, and sigma is larger than tau, then there is some element in sigma which is not in tau, such that, so say x, such that tau union x is also in I. So elements of I are called independent sets, and the maximal elements of the metroids are called the basis of the metroid. So the same simplicial complex can be described using non-simplices, using something called circuits. So again, for a metroid M on a finite ground set V is a collection of circuits C that are non-empty subsets of V, such that no proper subset of a circuit is a circuit. And if you have two circuits, C1 and C2, such that X belongs to the intersection of C1 and C2, then and they are different, C1 and C2 are not equal, then then C1 union C2 minus that common element contains a circuit. So this is how you describe the simplicial complex of a metroid using circuits, using a minimal non-simplices.